Alrighty, so I've got just a random collection of problems, notes I've done over the years. So I was just going to work out a couple of problems unless anyone has specific things you want me to work out. And if so, just say something and I'll pull it up and we'll try that together. And if I don't see anything going on, I'll just get started on my random collection of problems. All right, so let's start with the induction problem. And the one I came up with was this falling magnets. All right, so we're gonna have a falling magnet or loop. So here's the setup. We're gonna have a north-south magnet oriented this way. And we're gonna have a just solid loop here, just right. And we're gonna look at three cases and figure out the induced currents in this problem, all right? So find the induced currents in the loop in we're gonna do what's that here. Case one, loop is dropped. Let's see if I can spell dropped correctly. Loop's dropped. Case two, the magnet's dropped. In case three, both are dropped. So that's going to be our setup. One of these things will be falling or both of them. And then we're going to say, well, what's the induced currents in the loop? So let's do the falling loop. So I'll redraw the magnets. Add it north, south this way. Here's my loop. And let's draw the magnetic field. So north, south pole, what are they doing? The B field is coming out of the magnet, which means that they're going to loop around and do something like so. Right? So there's our orientation of the external. We have some velocity that direction for the loop because that's the thing that's falling. Right. So what do we identify? We need to say, well, what's the direction of this induced currents? Well, we need to figure out what is the EMF doing. So flux, start off with the magnetic flux. Magnetic flux is decreasing as loop gets away. Right. If phi b decreases, then the induced magnetic field points in the same direction as the external field. Right. So we're going to need to, I'll use green. We need to create a magnetic field that points in the same direction. So Scroll down a little bit. We're going to have this guy doing that. And it's so there's the induced again, direction of current that gets that. All right, right hand rules. For this one, you can get the same result with grabbing the wire. You just grab the loop and have your fingers curl the direction of the B field. I'm gonna go with my guy. So I'm gonna point direction of guess a current. I'll guess a current this way. Do that. So let's have I going that way around. Shoot. And that works. That does get the correct current. So yes, this works. And what I'll say is that if I'm an observer from down here, this observer sees, what do they see? They see a current going clockwise around. Yes, this is being recorded. All right. No other questions yet, so I'll keep moving. So let's keep going. Let's do part B. All right. In this case, it's the magnets dropping. So we'll redraw everything. Here's north, here's south. It's this guy that's moving now with some velocity. And here's our loop. So same magnetic field, they'll be doing something like this. Right. And now let's identify what the induce fields are. So as magnet drops, we need to say that the magnetic flux is increasing. Flux is increasing. All right. So then the induced field points opposite of the external field. So we'll just draw this again. So that means we have to have an induced field like that, which means that our current is going around counterclockwise. For, once again, the observer down here, what do they see? That legible. They see counterclockwise current. And we'll go on to our final case, C. Both are falling. And I hope it's pretty obvious, but I'll go through in detail anyways. North, south. Here's our loop. So here's what we observe. The distance between magnet and loop doesn't change. All right, obvious caveats in physics. We ignore stuff like friction, drag. We just say they're both falling at the same rate. Well, if the distance isn't changing, then the magnetic flux is constant. So no induced fields. All right. Let's keep this party going. Let's do more problems. I'm going to do some of the Snell's law and magnetism problem, geometric stuff. That's stuff we have had the least amount of time to talk about. So that's where my focus was. So let's shrink this down for a bit. Falling magnet in loop. And just put that in its own box. All right, next problem. All right. So here's going to be the setup. I'm going to give you 3 blocks. 1. Let's have them all stacked on top of each other. Come on. Let's go, buddy. There's our third guy. And now I'm going to shoot a ray through this material. So we've got in 1, in 2, in 3. And let's shoot a ray through. I'm going to have the first one come in at 20 degrees. Let's do this nice and high. So that comes in 20 degrees. Sure, all normal. Right. That's 20 degrees. That ray is going to refract as it goes from one medium to the next. And for this one, I went for, it refracted to 30 degrees. And there's our new normal. And then it'll refract again, but this time the refraction angle is going to be 10 degrees. Get rid of the ruler for now. So that was 10 degrees. This one was 30 degrees. All right. Question. Which material has the highest index of refraction? So Snell's law is pretty straightforward. We say N1 sine theta 1 equals N2 sine theta 2, where 1 refers to incident, 2 refers to refracted. All right. And I have a little shortcut that I like to use. Right? Instead of grinding out Snell's law, we can. There is enough information to just grind out Snell's law, explicitly calculate what the index values are. But I like my shortcut. If N1 is greater than N2, then the angles flip. Theta 1 is going to be less than theta 2. Or if it's the other way, if N1 is less than N2, theta, not 2, theta 1 will be greater than theta 2. Right? So this is the trick that I always reiterate to myself over and over again when I'm doing these types of problems, right? I set up a relationship at these boundaries and pull out the information. So let's go through this, right? Look at this boundary here. And what do we find? Well, don't know the indexes, but I do know the angles here. So if I call this, not highlighter anymore, I call this theta 1, call this one theta 2, then I can say clearly that theta 2 is greater than theta 1, which, using the rule in the box before, that means that N2 must be less than N1. Nice. So we'll box this off for now. We haven't finished the problem, but it's a step. So now let's do this guy, right? What are the incident and refracted angles? Right. At N2 N3 boundary. Well, the refracted angle is easy. That's a 30 or 10 degrees. Yeah, 10 degrees. Theta incident, question mark, question mark. Some of you might immediately recognize it, immediately identify what the incident angle is at this yellow boundary now. But I'll draw it again to be explicit. Let's bring our rulers back. There we go. All right. So here's our boundary. We have a ray that came in at 30 degrees. Right. Or, yep, that's 30 degrees. But we need to know the angle here now. Well, we can do just geometric extension, right? We'll extend the red ray, and then we'll identify our corresponding angles. And like I said, some of you might be able to just do this immediately. But let's go through the detail for those who need the practice. So not the refracted ray, right? Incident ray extended to do geometry. So extending that, I say, hey, look, I know this angle here to here. Well, that's the same angle. So this guy's 30 degrees. And if you flip across this axis, look, black to red, 30 degrees. Black to red is also 30 degrees. So we've used our geometry arguments to say that the incident angle at this boundary, N2, N3, is still 30 degrees. All right. So let's scroll back up. So I can say at this boundary, this is 30 degrees. And now we can repeat the incident refracted angles to get the comparison on the index refractions. So I can say, look, theta 2 is greater than theta 3. Therefore, N2 has to be less than N3. All right. Last step. How do N1 and N3 compare to each other? So all we've shown so far, we've shown that, let's see here, what? N1 is greater than N2, and N3 is also greater than N2. So how do we get how N1 and 3 compare to each other? Once again, we could take Snell's law and explicitly evaluate the index refractions. We do all that information, but I like to be lazy, and I like to show you smart tricks. So let's start to apply Snell's law, but not calculate it. N1 and 3 relationship. All right. So at the first boundary, you have N1 sine theta 1, that's the 20 degrees, into sine theta 2, 30 degrees. Then at the second boundary, we also have that into sine theta 2, 30 degrees, if you need the reminder, equals N1 sine, or not N1, N3 sine theta 3. We're at the second boundary, which is 10 degrees. All right, pull our smart little highlighter and we'll say, look, into sine theta 2 equals something. Into sine theta 2 equals something. So just combine the equations. And we'll find that N1 sine theta 1 is equal to N3 sine theta 3. So it's as if that there is no second boundary. It's just as if there's a refracted ray going from 1 directly to 3. And then we can use our previous tricks, right? Theta 1 is greater than theta 3. As a reminder, this was 20 degrees is greater than 10 degrees. So we have to conclude that N1 is less than N3. And therefore, N3 has the largest index refraction. Let's see here. Geometry practice. I'll box this one in. And let's come back. Let's see here. That is a fun problem. How about, let's see. Practicing geometry. We'll save that for the final exam review section. And let's do another Snell's law. Let's do a weird one. All right. This is going to be constructing a light pipe. All right, so here's our setup. I'm going to be making a device where I shoot a ray into it. I need the ray to hit the edge of this thing and get trapped inside. All right. So here's my optical device. And I'll make a nice right angle. And then it's going to make some angle here. This angle is going to be very important for us. What we're going to do is shoot in rays such that ray comes in, hits the boundary, and then gets totally internally reflected. Total internal reflection. All right. So we'll want to find that the refracted ray is just trapped in the prism. And therefore we only see the reflected ray. So let's draw the normal line. It's going to be about that. So here's the parameter that we're controlling. You have this angle phi. So this is an angle you control when you make the pipe. All right. And the question is, what's the largest possible value? What's the largest possible value for phi for total internal reflection? So that's our problem. Let's zoom in, do some geometry and some physics at the same time. So what I'm going to do is zoom in on this, right? I'll just redraw it. And we'll use a nice straight edge this time. Come on. So it does not have to be 20 degrees. I'm just doing this for illustrative purposes. We're going to have, let's do 30. All right. So that's the edge of light pipe. And we're going to shoot our rays in nice and straight. Once again, our refracted ray is just trapped in the glass. Now let's draw a normal line. Come on. Good enough. So here's the phi, and here's our incident angle. I'll call it I. And we know what this is. If this is the refracted angle, you know, this must be 90 degrees. So once again, for the ray to be trapped, the refracted ray is at 90 degrees. So we can say Snell's law. In whatever the pipe is, let's go back a bit to clarify. We're going to have, we'll have in pipe. This part we're going to call it 1.6. Out here we have in air, which we're calling 1. So at this incident, we are in pipe out to the air. So our Snell's law is going to be in pipe, sine of whatever this angle I is, the incident angle. It's going to be equal to in air, sine of 90 degrees. All right. Don't particularly care what I is. We want to figure out what phi is. Or I don't want to do this. Let's see here. Into that's going to get I is the critical angle. I want to figure out what phi is. So 2 routes, right? Phi. Option 1. Use the above equation to get what I equals, and it'll be some number. I didn't calculate it. Then use geometry. You get phi. Option 2, which is the option we're going to use. Both routes are equal. I just don't feel like calculating the incident angle I, since we really don't need it in this problem. So use geometry to replace I in above equation. And to be specific, I mean this guy. Right. Use geometry to replace I in above equation. So we're going to use this method. So what do we need to do? We need to figure out how phi and I relate to each other, right? Hopefully it's pretty obvious. If phi is this trajectory, I is measured with respect to the normal. Hey guys, I'll use orange to highlight it. A bit bigger. That's a 90-degree angle. So you can just say phi plus I equals 90 degrees. Or that incident angle, whatever it may be, is 90 degrees minus phi. All right. We'll so then do our box equation. We now have the index of the pipe, sine of 90 degrees minus phi equals NA sine of 90 degrees. All right. NP as is, sine degrees minus phi, just equal to NA. Sine of 90 is just 1. All right. So now solve for phi. So I'll divide by the index of the pipe. Sine 90 degrees minus phi equals whatever this ratio is. Take the inverse sine. Or the arc sine as I prefer to write it. NA over NP. All right. Add phi across, subtract the arc sine. Phi is equal to 90 degrees minus arc sine NA NP. Plug in some values. Arc sine NA was 1. The tube was 1.6. So it'll be 90 degrees minus, I got 38.7 degrees. As a reminder for everyone, make sure your calculator is in degrees mode. Way too many people lose lots of points because they calculate with radians versus degrees. Make sure you know the difference and make sure you're using the correct calculator setting. Right. So finally, we find that we can engineer the pipe to have that angle, that bend in it, that slot down, to be at 51.3 degrees. Got time for one more, so I'll shrink this down, box this problem up. All right, this one I pulled straight out of the textbook. This was problem in my notes, problem 23.15. This is one about electromagnetic waves. So here's the problem. I'm just gonna rewrite it down, right? Problem said, write the equation, write the wave equation for the magnetic field it's traveling in the negative x direction. As a wavelength of lambda equals 2.0 meters. And the wave has a electric field maximum of 100 newtons per coulomb. I'll rewrite that as how we've gotten the convention of writing fields as volts per meter. Same thing, newtons per coulomb, volts per meter, identical units. All right, so that's the problem setup. Write the B field expression for this thing. So, as a reminder, the equation would be something as B of Tx equals some B max sine of omega t minus plus kx. All right. That's the general equation. And now we just gotta fill in the bubbles. We need B max, omega, and k. Let's start here. You get U, 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 and the sine. Right. So let's start with the sine. Let's just go left to right. All right. B max. B max. You might recall there's a relationship for waves, for electromagnetic waves. This must be true. E equals CB. Right. This must hold for electromagnetic waves. So we can just say, look, B max is equal to E max divided by C. And the problem gave that to us. So this is going to be 100 volts per meter divided by speed of light. That's 3 times 10 to the 8th meters per second. All right, this is going to be 1/3 times 10 to the minus 6 Teslas. Or 0.333, however you want to write this. So I wrote it as 0. I just wrote two decimal places. 0.33 microtesla. All sorts of equivalent ways to write this. All right, next part. We need omega. All right, omega, that is the angular frequency. And it's related to the regular frequency as 2 pi f. All right. But we have lambda, not the frequency. So we need to convert our wavelength to frequency, then our frequency f to the angular frequency. So just a few more steps. C is equal to lambda times f. Must be true. If you do not remember this equation, you're gonna fail this test. Like, not even joking. Like, this is a fundamental rule of just our universe. So C equals lambda f. So we can just find the frequency directly. F is equal to C over lambda. Now just plug it into our omega. Omega is 2 pi f. I don't care what the frequency is, so don't waste the calculator time crunching the numbers. Just plug it in. All right, this is 2 pi f, then this is 2 pi c over lambda. More space. So this translates to 2 pi times 3 times 10 to the 8th meters per second divided by our wavelength. We said our wavelength was 2.0 meters. So our omega is going to be, let's see here. I see a 2. Let's see, there's a 2 here. There is a 2 here. Cancels out. 3 pi times 10 to the 8th inverse seconds. If you want to be pedantic, this is technically a radian per second, but radian is this dimensionless quantity. Right. So scroll back up, just double check what we have. Let's see here. Done, done. Need the sign. Sorry, it's a minus plus term. All right, this is just a rule you have to remember. You can think of, go back to the lectures where I did the plots of, do you minus or add to shift the plot of the function? All right. And I'll just tell you now, a plus sign corresponds to a wave traveling in the negative direction. Right. So last one. Boom. So now I just gotta get the wave number. That's the last guy left. So wave number. Okay. Straightforward, it's just a 2 pi over lambda. So 2 pi over 2.0 meters. It is going to be pi inverse meters. All right. Plug in all of our ingredients. Our magnetic field equation is going to be 0.33 microtesla sine of, how did I write the omega? I wrote as 3 pi times 10 to the 8th inverse seconds times time plus a pi, that's inverse meters, x. All right. There's one of our sample electromagnetic field problems. All right, guys, I'm going to call it an end of the review session here, unless anyone here has any specific questions they want to ask now. Otherwise, take care. Good luck studying.
Thank you.